Hello everyone. My name is Monalisa Chakraborty from Texas A&M University, and today I'll be presenting the paper titled Rethinking the Generalization of Drug Target Affinity Prediction Algorithms via Similarity Aware Evaluation, which was accepted at ICLR 2025. This is a part of Journal Club presentation for the course Algorithm for Structural Biology. Okay, so before digging deep into the topic, I would like to briefly explain about DTA or drug target affinity. So basically, DTA refers to how strongly a drug molecule binds to its biological target, like a protein. This is typically quantified in biology using matrices such as IC50 value, Ki value, or binding free energy values. So basically, a high DTA means high drug potency or specificity. Therefore, early prediction of DTA will help streamline drug discovery by reducing the number of compounds that needs to be tested experimentally. So as we have understood the uh, topic, so here the general topic is to use machine learning to predict the DTA values. The specific issue which is addressed by this paper is that the current evaluation methods often rely on random dataset splits, which basically overestimate the model performance. This happens because these random splits include mostly high similarity molecules in both the train and the test sets. As a result, the model struggles to generalize to low similarity or novel compounds. So we can see that this is a serious concern for drug discovery. If the model can't generalize to novel molecule, their utility in real world drug development becomes questionable. So, we would need a robust model which performs well even on low similarity compounds, since these are typically the unexpected uh, candidates of research in candidates of interest in pharmaceuticals R&D. So, to understand the current state of art DTA prediction model, uh, which includes SAM DTA, Pharma GHT, Chem Berta, and Fusion DTA. All these models are often benchmarked using random or scaffold splits. Unfortunately, as discussed previously, these splits still favor structurally similar molecules, and the train and the test set have like similar kind of molecules. So this leads to inflated matrices that do not reflect a model real generalization capabilities. So this is the catch the where we figure out the key gap uh, in the existing evaluation as the existing evaluation approach failed to adequately test model on low similarity compounds, which are the most important in real world application. So without stress testing models on such samples, we cannot just fully rely on the generalization claims. Therefore, the author in this paper has proposed a framework which is called the Similarity Aware Evaluation, or more specifically SAE. It formulates test set selection as an optimization problem to match the desired similarity distribution. So, the overall goal is to more accurately assess a model's generalization by including low, medium, and high similarity samples in a very controlled way. So in this slide, we'll see the approach or the method that has been used to uh, explain the paper well, or um, how this method is working. So let me explain how SAE works in a simple way. So the main idea here is to split the test set in a smarter way, not randomly, but based on how similar test samples are to the training samples. First, the method defines how many samples should go into each similarity group, as I already mentioned. So instead of assigning test samples manually, it treats uh, it treats it as an optimization problem. It adjusts the weights on each sample to decide whether it should go into the test set or not. For this, it uses various mathematical tools like the log sum uh, so what this does is approximate the maximum similarity without using hard max function, which aren't good for optimization. It also uses soft max binning, which helps assign each sample to a similarity bin smoothly instead of sharply. It also uses entropy regularization, which pushes the weight closer to either 0 or 1 so that the samples are clearly either in the test set or not. Gradient descent is also used to minimize the bin matching loss. Finally, test set matches the intended similarity distribution, improving evaluation. So this is the generalized proposed method that has been used for this paper. Next, let's discuss the results. So here we can see that the figure or the result compares two set of splits. One is the random split and the second one is the SAE split. So this data set is of the IC50 value of target EGFR with a total of 4,361 samples, which is one of the largest data set that they were able to find. As I already mentioned, this shows a side-by-side comparison between the random split and the SAE balance split. As you can see, the random split make model look good because over 88% of the data set is similar to the training set, which is bias. So basically, we do not want that bias, which is handled by using the SAE split. So what the SAE does is it will split the data uniformly. So here we see that the SAE is more balanced. It has more balanced splits, which and we can see that the performance metrics drop, especially for the lower similarity bins. This shows that the SAE is better at revealing how model behaves on difficult and real world scenarios. So the model For the model, the matrices that has been used for analysis is the MAE, which refers to the mean absolute error. It measures the average prediction error. So the lower the MAE, the better the results. It also uses the R square value, which which measures how well the model explains the variation in true value. In this case, the higher the R square value, the better the results. So we can see for the random splits, it has like higher R square value and higher R square value and higher MAE value. Lower MAE value. Whereas for the SE split, we see that there has been an increase in the MAE value and a drop in the R square value. Okay, so they have also compared the similarity distribution across uh, 5 splitting strategies. Here we can see that only the SAE mimic split successfully mirrors the distribution of a real-world external test set. This confirms SAE's ability to create evaluation conditions that are more realistic and meaningful. Okay, coming to the conclusion and critique, this paper successfully demonstrates the most current DTA evaluation setups are misleading. essay addresses this by enforcing similarity aware test set design. Coming to the limitation includes optimization complexity and the need for parameter tuning. And for future work, this could also be expanded to other domains like admit prediction or protein-protein interaction modeling as well. That's all. Thank you so much for patiently listening to my presentation. And if you have any question, you can leave a comment on the comment section.